Hello and welcome to ML6's Hammertime, a series where we make fun little projects you can do in a weekend and try to over-engineer them in such a way that we can use machine learning to do them. It might not be necessary, but we can learn a lot along the way. Now, probably similarly to many of you, I've been working from home a lot, and well, my office is in the attic, so I don't always hear my doorbell when it rings. And as you might know as well, there's a lot of packages being delivered these days. So I would like to know when someone is at my door and get the package, but right now I can't. Now I know it's a lot easier to just get a Ring doorbell or like one of these plug and play doorbells, or even just put a sticker with my number next to the door. But I don't want to do that. I want to use machine learning because I get to learn a lot more about signal processing and audio processing and make something cool along the way. Now, in terms of hardware, there's not that much you need. You need a Raspberry Pi on the one hand, or some similar device or board that you can use to do the processing on, and then on the other hand, you will need a microphone or a USB webcam with a built-in microphone. I did it with a relatively old, inexpensive webcam, and in this case, actually, it might be the better choice. Because usually one of the selling points of more expensive hardware is that it has some kind of built-in noise reduction, and that's exactly not what we want here, because that's exactly what we want to detect. Background noise. Now, once you have the Raspberry Pi and then the microphone or webcam attached, you can start gathering data. The recording of this data is relatively simple. You need only two things. You need one audio file that is filled with what is called ambient noise, and this is kind of normal sounds that happen in your house. Put the Raspberry Pi and the webcam where it's supposed to be, let it record for a while, and then just walk around your house. Vacuum clean for once. Start a washing machine, start a dishwasher. Walk around, shout to each other. Things like that. Do anything but ring the bell. So now that you have the ambient noise, what you'll need as well is examples of the doorbell ringing. So take your time to do this well, and you don't need that much. Ring it and then wait for it to silence down, so that later we can cut that piece out, and then ring it longer, ring it shorter, ring it more than once at the same time, like your in-laws are at the door. Once you have the data that you need, which is two files, one ambient noise, the other one examples of the doorbell ringing, we can go to the next step, which is actually processing the raw data. Alright, so pre-processing the data. Now, the first thing you need to know is that the kind of machine learning we're doing here is actually called audio classification. And what we want to do with that is we want to say for a specific part of audio, does it contain a bell or does it not contain a bell? These specific pieces of audio are called windows. And what we want to do is, out of our examples of different bell sounds, we want to create multiple windows that include bell sounds and multiple windows that do not include bell sounds. This part I actually did manually. So I went into Audacity and I loaded up my bell sounds file. I cut up the different kinds of bells that I recorded, and then I just exported them all as MP3s. To get that same size of half a second out of the other pieces of bell sounds as well, we can use what is called a sliding window approach. Imagine you have a 2-second audio clip and you want to take half a second windows out of it. The easiest way to do it is to take the first half a second, then the second half a second, third and fourth. That is what is called a sliding window approach. You can also do this with a smaller step. So now we only took the beginning of the next window where the previous window ended. You can also do overlapping windows so that you can get a little bit more data out of your audio files. So now that we have all of these windows containing bell sounds with equal length, we already have the positive side of our dataset. And we have to do the same thing for the ambient noise. This is quite easy. You could do a sliding window over the whole 1 hour of the audio file and have a lot of windows for ambient sounds. But out of experience, I know that a lot of the ambient sound is actually silence. Nothing happens there. So you can actually use the awesome library PyAudio Analysis to get the silence out first. and then we are left over with the interesting parts of our ambient noise and do the sliding window approach on only those pieces. Now to recap, we had our Raspberry Pi attached to our microphone or webcam, and we recorded ambient noise and bell sounds. Then out of each of those files, we got our sliding windows, and now we're left with a whole bunch of windows containing no bell sound and a whole bunch of windows containing bell sounds. This is our dataset. So a normal microphone actually records at 44 kilohertz, which is a lot of data. It's 44,000 data points in a single second. So if we can then look at our window size of half a second, we would have 22,000 points for a single detection. That seems like a lot. The machine learning model will have to take into account all of those points to make a good fit, which usually means you need a whole lot of data to support this. But we don't want to record and then manually extract hundreds upon hundreds of bell sounds. So we can actually just make features, which is an easy way to get the useful information out of these 22,000 points into maybe 20. One such feature is called MFCCs, or Mel Frequency Capstral Coefficients. MFCCs are used so widely and so successfully that even deep learning models, which usually create their own features based on the data, are actually fed MFCCs instead of the straight raw data. These features are very, very interesting. They're mathematically quite complex, but they're also modeled in such a way as to replicate how our ears perceive a certain sound. These coefficients are calculated using 5 distinct steps. In the first step, we're going to take our half-second windows and split them in even smaller windows. Now we want the windows large enough that they capture a meaningful amount of data, but also small enough that the signal doesn't change too much within that window. The second step is to take this piece of audio and apply the Fourier transform over it. The Fourier transform will take this piece of audio and decompose it into a whole bunch of overlapping single frequency waves. Now, we end up with a graph that tells us exactly which of these frequencies are in this piece of audio, but also how loud each one is, which is the power in power spectrum. Now, if we look at this graph from the top and we assign a color scale to the loudness of the frequencies, we actually have the first line of what is called a power spectrogram, which is a visual representation of the power spectrum. Now, the only thing left to do is to do this for every single small window in our half-second window. And we end up with a full power spectrum, which you might have actually seen before. Now that we have our power spectrum, we want to apply the MEL filter to it. Now the MEL filter is really interesting because it goes out from the biological idea that what we as humans perceive as frequencies being far apart or close together doesn't necessarily align with what is mathematically close or far apart. That's what the MEL filter does, is it realigns what is mathematically equal in distance to what is actually equal in perceived distance. Now the fourth step is to take the log from the result. This is again rooted in biology because we as humans don't perceive loudness as being linear. So the difference between two very loud sounds is not the same for us as the difference between a quiet sound and a very loud one. The final step is that we use the DCT, or the discrete cosine transform. This is used because the overlapping windows, remember, that we used to do the Fourier transform on, are overlapping, and so they're highly correlated. The DCT gets rid of that, and it also gives us the coefficients from MEL frequency capstral coefficients. After all of these transforms, we usually keep 12 or 13 of these coefficients, and we can use those as our features. So now the fun part begins, the machine learning. Using Sklearn, the Python package, we can actually do a whole bunch of things relatively easily. So we start off with putting all of our data on the same heap and cutting it up into a training set and a test set. We're gonna go pretty default here, so we're gonna use a 20% test set and an 80% training set. We're gonna leave the test set alone for now, and we're gonna focus on our 80% to get our machine learning models running correctly. We're going to use an sklearn function called grid search CV. And so it's two parts here. Grid search is actually a way to search for the optimal parameters given a set of possible parameters. And then you have the CV, which is cross-validation, which is the way we're gonna evaluate whether or not a certain set of parameters is a good fit. Next, Sklearn goes through all of the performance metrics for all of the different parameter combinations and then picks the one parameter combination which gives us the highest performance metric. Just like that, we have our machine learning model trained, and in our case, it was very good. Now the fun part isn't over yet. So now we get to take that machine learning model that was trained before and put it back onto the Raspberry Pi so that it can do its thing continuously 24/7 and monitor when a doorbell happens and let me know too. Now we're going to do this using a relatively simple design pattern called a producer-consumer system. And so what this means is that you have several tasks that run at the same time and they actually put everything in a queue for the other to handle off. So there's actually going to be 4 main parts in our producer-consumer system. So the first thread is going to continuously record audio from the microphone or the webcam and process it into windows of 0.5 seconds long and put it into the queue. Then from that queue, a second thread will take those windows and pre-process them by calculating our MFCC features. Those features end up in a second queue. That second queue will be read by a third thread, and that thread will actually take those features and run the machine learning model. The model will return a 0 or 1, either it being a bell sound or it not being a bell sound. Those zeros and ones end up in a last queue. And the last queue is actually just read by a pushover service that can send a notification to my phone or to my tablet if a bell sound was registered. Pushover is a cool service that allows you to send notifications to your phone, tablet, or even computer using just a post request to an API. That's pretty much it. Now we have gathered our own data. We have pre-processed it, we have trained the machine learning model, and we have crucially also deployed the machine learning model on our Raspberry Pi so that it can be used on a daily basis. Now this system is far from perfect. There is so much more to do. So we're going to do 3 things in the next video. One is we're going to better deploy the machine learning model to our Raspberry Pi using Docker and Docker Compose. The second thing we're going to do is we're going to create a dashboard using Plotly Dash in which we can see every single time that the model has triggered and then relabel those as being correct or wrong. So then we can use that data for the next part, which is making an automated retraining pipeline so we can continuously make our system better. Now, if this isn't over-engineered, I don't know what is. Hopefully see you next time, and thanks for watching.